Welcome. In this video, we'll take a look at the concept of angular velocity. So let's take a look at the definition and then we'll roll through with a few examples. So angular velocity, we can consider if P is a point moving with uniform circular motion on a circle of radius r, and the line from the center of the circle from P sweeps out at a central angle of theta in an amount of t or a time t, then the angular velocity we are going to call omega, this value right here, this is omega. The velocity of p is given by the equation omega is equal to theta divided by t, where theta is measured in radians again. So when we consider angular velocity, what angular velocity is saying what is the turning speed of a given point. We're actually not concerned with the radius of a given value or circle, but we're just thinking about how fast can we turn our point. And so our measurement here is just going to be radians per time measurement. So let's consider the first example here, and we'll jot down our omega is equal to theta divided by time. So we can consider the first example, a point on a circle rotates through 3 pi over 4 radians in 3 seconds. Give the angular velocity of p, this point. And so in this case, our omega is just going to be the angle that we travel. That's 3 pi over 4 radians divided by 3 seconds. And so here, if I divide by 3 seconds, there's really some threes that I can cancel here in my calculation. And so we'll be left with just pi fourths radians per second. So it might be a good question to answer here. What is the connection between the linear velocity that we've talked about before and this angular velocity in terms of a circle? So here's where we're going to break down the relationship between the linear and the angular velocity. So we're going to play with a little bit of the terminology we used in the past lecture with the arc length as well. So we know that the arc length s is going to be the radius times the angle theta. So we have that same diagram from before. And we know that the velocity v, the linear velocity equation, is v equals s over t. But we know that we can say that we can rearrange this equation for s, and so that would be saying that s is equal to v times t. Now, notice that both of these two equations have the arc length s. And so we can set those two equations equal to each other and get a new equation. So we know that r times theta is equal to the velocity times t. And so we're going to set those equal to each other. That's what we have in our next line. We can say that the v times t is equal to r times theta. And therefore, when we go to solve for v in this equation, we know that v, the linear velocity, is equal to r theta divided by t. But one more connection we can make here is that omega was just theta over t, which we have right there in our velocity equation. So the linear velocity and the angular velocity can be connected with this same formula, where theta divided by t is omega, and so the velocity, linear velocity here specifically, the linear velocity, get back to my page, is equal to the radius times the angular velocity. So that was a lot of work, but that is how those two items are going to be connected for us. Is the linear velocity is equal to the radius times the angular velocity. So we know that v equals r omega. So we can use this in a lot of our calculations where we need to find both the angular and the linear velocity. So let's take a look at an example for this. Again, we know that the linear velocity is equal to the radius times omega. So we can use that in future problems. This example says a woman rides a bicycle for 1 hour and travels 16 kilometers. We want to find the angular velocity of the wheel if the radius is 30 centimeters. So a few things we want to be aware of here. One is the units of our calculation, and one is just how do we calculate this problem. So let's consider first the bicycle wheel. So a woman can ride a bicycle for 1 hour and travel 16 kilometers. That means her linear velocity, v, we can rewrite as 16 kilometers per hour. That would be her linear velocity. And we'd like to go out and solve for the angular velocity. So we know the v, linear velocity, and we know the radius of her wheel, 30 centimeters. But notice that both of these measurements here are not in the same units. So we're going to have to work on that. One thing we could do is just convert both of these to meters. So we can work in meters. And so we know that the radius here is 30 centimeters. If I'm 30 centimeters, another way to write that is we're going to be equal to 0.3 meters. That's the equivalent conversion to meters. And if I wanted to convert my speed here, the velocity, to meters, I'll just do a conversion table real quick. We'll clean this up just a little bit and give this a conversion. We know that 1 kilometer is equal to 1,000 meters. And so we can say that 16,000 meters divided by 1 hour. So let's set this final equation up. We know that v equals r times w. So v here, the velocity is 16,000 meters per hour, is equal to the radius, which is 0.3 meters, times omega. And we'd like to solve for omega. If I solve for omega by dividing by 0.3, we can find that this is going to be 16,000 divided by 0.3 meters per hour. To clean this up a little bit, we can just write this as 160,000 over 3, just to keep it as a exact solution. This doesn't look like it divides evenly into 3, so we can just leave it as this. And so We'll take this in meters per hour. Will be our result. And this will be our final conclusion. So units are really important on our problem. We want to make sure that we have those down. In the next video, we'll take a look at some more examples relating both the linear velocity and the angular velocity. Look forward to seeing you in the next video.